Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we have this lecture to finish on data models, and then we'll move over to data frames and MapReduce. But before that, I have one question for you, which is this question. So this is a document, and I'm asking you if it is well-formed only, or valid only, or well-formed and valid, or neither of those. I'll show it to you, the document again. Is it well-formed or not? Is it valid or not? Have the first votes coming in. Right. There are many more people than votes, actually. So on Zoom, you can also participate via Edu app, right? Everybody can participate. All right. Aha. We had well-formed only and well-formed and valid. So it is well-formed, indeed. If you look at it, that's a perfectly fine document. There's the XML declaration, doc type ETH that corresponds to the top-level element. This is good. That's an attribute, that's nested text, nested element, and so on. So it is indeed well-formed. But can anybody tell me why it is not valid? Why you cannot say that it is valid? Anybody? On Zoom, maybe. Does anybody know why I cannot say that it's valid? Exactly, we are missing a schema. The validity can only be assessed with a schema. If you don't have a schema, then you cannot say anything about validity. You can only say that it's well-formed. So now this is XML. I haven't shown you how the schemas look like, but you will see it's pretty similar to JSON. Okay, so remember, well-formedness, that you can always say, yes or no, it's well-formed or it's not, it parses or it doesn't. Validity can only be assessed with a schema, and it even depends on the schema, right? If you change the schema, then you might change also whether it is valid or not. Okay, so now I'm going to show you XML schema. Well, not all of it, I'm just showing to you the basics so that you get the idea of it. So let's look at it. Let's look at one. On the top of the screen, I do it similar to what we did for JSON. I have what is called an instance document. This is a document that we know is well-formed, right? If it's not well-formed, then we would have stopped anyway, so it is well-formed. And now I'm asking the question, is it valid against the schema that you have below? Because again, you need a schema for validity. So is it valid against the schema that you have below? But let's first take a step back and look at what's going on here. This schema, what syntax is it in first? It's XML, right? It's exactly the same idea as for JSON schema. The JSON schema was in the JSON syntax. The XML schema is also in the XML syntax. Of course, it doesn't have to be, right? It could have been different, but it turns out that we use exactly the same syntax. Now, what do we have in this syntax? We have specific elements that are the the elements that are used by the schema. It's a language, right? It's the XML schema language. It's a specific XML syntax. And all of the elements that we use in the schema, in the attributes, they are predefined somewhere. It's specified fully. And it's easy to spot them because they are the ones that start with XS, right? So you see XS elements, they are XS schema, XS attribute, and so on. We nicely put them in a namespace. The namespace, think of it like a Python module or a Java package or something, right? We didn't get too much into the details of those. But basically, we use these specific elements of the XML schema specification in order to declare our schema. It was a bit the same in JSON, right? You have, for example, in JSON schema, you have the JSON keys. There's the JSON key that's called required, another one that's called properties, another one that's called additional properties. These are also defined in the JSON schema specification. So it's the same thing, right? Okay. So we have a schema. There's always an XS schema at the top level, right? That's the namespace. And then we declare here an element, the name of which is foo, and the type of which is string. What does it mean? That name here is the name of my element right there. The name is foo. The type is string. What does it mean? It means that this here must be a string. Is that the case? Yes, that's the case, right? This is a string, right? What we would not allow, for example, is nested elements in there, right? Because that wouldn't be a string. But here it's a string. So this instance document is valid against that schema. Who is with me? All right. Now, don't be scared. The XML schema is a bit verbose, it's a bit complex. But the nice thing is that when you actually do a schema, you often do it with Oxygen, and Oxygen has this autocomplete. It automatically tells you what you can put where and so on. So this is often computer assisted when you define them, right? So it can be very verbose, but there is no reason to be scared. Here's another one. Do you see the difference? What I changed is the type. Now the type is no longer string, it's integer, right? So the integer, is it an integer? Yes, because you need to look at the lexical value 142857. This is in the lexical space of integers, right? You can pass that as an integer. So this is fine, right? So the type is an integer. Who agrees? Okay. Now, here's another one where we have nested structures. So here we have a child element last and a child element first. Both of them are strings, right? So last and first would be strings. So you see the corresponding declarations. Last is a string, first is a string. But we need to embed them into a type. So we say that we have this element person right there, which is a complex type. And that complex type is made of a sequence of these two elements, right? The order is very important. If you don't specify otherwise, then it must appear once, and that gives you a valid document, okay? So what you see is that there's always this top-level XS schema elements in the schema, and then you declare your elements. Some elements are at the top level, and some elements are nested inside other elements, and this is what it looks like. So the document that you see at the top is valid against the schema that you see at the bottom. And again, last and first have a simple type, string, an atomic type, but person doesn't have an atomic type. It has a complex type because it's made of a sequence of elements. In fact, if you're familiar with Java or these kind of languages or C++, it's a bit the same as distinguishing between the atomic types and the object types, right? So person would basically, if you were to map it to Java, there are ways to map it to languages. Person would be an object, and last and first would just be strings. Okay. All right. Here's another one. So the new thing in there is the min occurs and the max occurs. You can actually change the number of times that each one of these elements appears. So you see the 2 to 4 element has a min occurs of 2 and a max occurs of 4. It means that it can occur 2, 3, or 4 times, right? Is it the case? Yes, it's 3 times there, and 3 is between 2 and 4, so that's fine. And 0 or 1 has a min occurs of 2 and a max occurs of 1. it's there once, so this is fine, right? It's also in the bound, right? So this document with repeating elements is valid against that one because I allow the repetition and I control the number of times that it repeats. It's very similar to what I told you that in JSON schema, you can also control the number of times that the number of members that you have in a JSON array, right? So here too, you can control that number. By the way, just to simplify, now I'm dropping this excess schema, blah, blah, blah. I just only show the relevant part of the schema to not overload my slides, right? So this complex type here would be the complex type for foo and would have to go inside an element foo, right? But I just show the complex type. Okay, so now you know how to declare elements that have an atomic type. You know how to declare elements that have a list of children elements inside. Now, what about empty content? You have many ways of doing that. The easiest one is to just declare a complex type, which has a sequence, but then you don't put anything in there, right? So you see here, the sequence has 2 elements. Here it has 2, and here you just leave the sequence empty, and that's it, right? So that's how you declare it. How do you support mixed content? This is something you cannot do in JSON, but in XML, you can actually have text that is interspersed with elements. This is specifically useful for the publishing industry, where you are going to have scientific papers. And then in these papers, you tag sections, subsections, bold, italic, and so on, like these kind of things. So this is why you need that kind of mixed content. How do you do it? It's actually easy. You only need to put this mixed equals true attribute in here. You see, complex type mixed equals true. And these are the magic words that allow you to have some text in addition to the children element. If you did not have mixed equals true, you would only have this allowed, the B, but without the extra text in there, right? So this is what the mixed equals true gives you, right? If mixed is not true, like in here, you cannot have text before or in between the elements, right? You must have directly the elements and nothing else. Okay. Now you can also validate attributes. And the way you do that is that when you define your complex type, you have the sequence of children elements, last and first. And right after the sequence, you add an excess attribute, the name of which is birth, and the type of which is date, right? So this, yes, there is a question over there. Do we have the catch box maybe? That people on Zoom hear you? There you go.
No, just on the one before, I was wondering why foo wasn't defined in the mixed type.
What is defined? Oh, foo.
Yeah, just the foo, like the general one.
Yes, you're absolutely right. It's just that I'm only showing the complex type part. That's what I said. It's just to keep the slides easy. You would need to have this excess schema, excess element named foo, and so on. And you see the complex type. That's only that part that I'm showing here.
Yeah,
that's the reason, right? Yeah. Just because otherwise the slide would be enormous. Yeah. Right? There you go. Thank you. Okay. So yes, so the attributes. Now you see the way you validate an attribute is similar to how you validate an element with a simple type. You have this name in this type, and that's it, right? The name is birth, the type is date. How do you validate? This is here the lexical value. It's just text, right? But since you now say it should be a date, then you check, is it a date? Yes, because you have digit, 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 dash, digit, digit, dash, digit, digit. So yes, that's a date. And after the validation and annotation, this will be an actual date in the memory. Now that this excess integer, excess string, excess date, that's part of this menu that I showed you earlier, right? It's the same list of types for XML schema as it is in JSON, as we will see is in JSONic and so on. It's exactly the same list of types. Okay. Here's a concrete example. Do you remember this great language game that I showed you in JSON, where people have to guess the language in which they hear a recording? I just converted it to XML. It's a JSON data set normally, but I just built an XML equivalent where you have the games and then game, and then inside you have guest, target, country, choices. I just try to do it in an equivalent way in XML. There's not necessarily only one way of doing that. There can be several, but here that's one sensible way of doing that. And you have on the right this schema. Don't be scared. Again, it's very verbose, but actually, if you look at the details, it kind of makes sense, right? Let's look at it together. So you always have this excess schema, the top level. Then you have these elements, games. That's the top level element that you have here. Then it's a complex type with a sequence. What we have inside is game, right? Below games, there is game in the singular. It's a very common pattern to have a plural form here and then a singular form for the repetition. So we say game and max occurs unbounded. This is how I say I can have as many million games as I want in there, right? So this is unbounded. Then if we look at game, it's a complex type with a sequence. What do we have inside? Guest, target, country, choices, date. Guest, target, country, choices, date, right? So we list them. Guest, target, and country, these are just strings, you see. Choices, that's a complex type. So choices, we must say it's a complex type with a sequence. Nested in there, it's again this plural form, singular form idea here, where I have choices, that is again a complex type, a sequence. Here we have choice of type string. Here it's just a string. Max occurs unbounded. You see, you can have, technically it's 4. I didn't do it. We could also add some constraints that say it's exactly 4. Date is an excess date. So yes, that passes as a date. And the attribute sample of type excess hex binary. It's this sequence of bytes, but in base 16, right? So you see, this is in the lexical space of hex binary. So that's my schema. Do we have a question on Zoom? I think I saw.
Yes, there is a question asking why is it complex? Yes, it is asking why it is so complex.
So complex means that you don't have just text, but you have nested elements, right? So for example, this guest, target, country, choice, these are all just strings, right? So this is called a simple type. The element has a simple type. Date also has a simple type here, but choices is complex because it has nested elements. Game is complex because it has nested elements. Games is also complex because it has nested elements, right? So simple means there's just text and you try to parse it as a specific atomic type. Complex means there are nested elements, right? Okay, does it answer your question? Then I'll come to you on Zoom.
Yeah.
Yes, okay, go ahead. Yes, that's a good question. So mixed equals true means that you mix text and elements, but at the same level, right? So that's the reason. Here, there is indeed text here, but that text appears nicely in between element tags, right? Mixed would mean that between guess and targets, there would be something. Here, in between, there would be text. In between, there would be text. In between, there would be text. And in between, there would be text at the same level of the elements. Then if there were text between these tags, then game would be a mixed type, right? But here it's just not mixed because there are only elements as direct children. It's really, again, the direct children and not all the descendants, just the direct children. All right. And this is the geeky part because I love these things. The schema is itself an XML document, right? And so you might ask yourself, can we also validate the XML schema against another XML schema, right? What if now we consider that on the right, this is an XML document, and we try to build a schema for the schema on the right, right? And in fact, yes, the answer is absolutely yes. There is what is called the schema of schemas. There is an XML schema, and basically it validates all the schemas, so all the schema documents seen as an instance validates against the schema of schema. But what's beautiful is that the schema of schema validates against itself. This is beautiful. So this is the instance and the schema at the same time, right? You can see if you look closer, you have an element that's called schema. That's the one right there. Then you have, it's a complex type and so on. You have an element called element that is itself actually, the type of which is top level element, which is defined somewhere else. Then you have the element complex type, that's the one that we saw, complex type right there. So there is a meta level of the schema of schemas. So here it's very theoretical. This is not really something you need to worry about. It's more like a curiosity. And by the way, the same goes in JSON. You can also have a JSON schema that validates all JSON schemas. You can also have a JSON schema that validates all JSON schemas. So again, just for your curiosity, I'm showing you that. Okay. But again, what do I want you to remember from XML schema is that it works pretty much the same way as JSON schema. The paradigm is slightly different because it's about elements and attributes rather than about objects and arrays. But the idea is the same. So now you can force in an XML document the text to be of a specific atomic type. You can force the elements to have a specific children in a specific order and with specific names and a specific repetition, and so on and so on. Okay, so there will be exercises to train you a little bit with that. We don't go really into the deep details because XML schema can be very complex. The goal is just for you to understand what it is to validate the documents against the schema, and that this is really about constraining the structure of the documents. And typically, when you have a schema like that, you don't just validate one document. You typically validate millions of documents, right? So you have a collection with 1 million documents and a single schema, and you want every single document in that collection to be valid against the schema, right? This is the idea, okay? All right, so now I'm going to link it to data frames. Now you can forget about XML because this is really the JSON part that I'm linking to data frames. I think I already asked you, like, who knows pandas data frames? Who already heard of that? Okay, so this is what I'm now linking it to, but now you're going to have a theoretical understanding. Need to remove the text bar right there. There. So what I want to show you is that a data frame, in fact, is nothing else than a collection of valid JSON documents. That's what it is about. So I'm going to show you. On the left, what do we have? It's a JSON schema. What we accept with that schema is JSON objects that have 3 optional keys, ID, name, and living. ID must be associated with some integer, like 42. Name must be associated with any string. And living must be associated with either true or false, a Boolean. So this is a JSON schema. You can use that JSON schema to validate 1 JSON document. But what if you validate 4 JSON documents? Imagine you have 4 JSON documents. They all have an ID, name, and living, and it fulfills these types. Do you see that, in fact, what you see on the right is pretty much that, but in a visual way, right? On the right, I have, it's actually a data frame. It has 4 records. In the first record, the ID is 1, the name is Einstein, living is false. In the second record, the ID is 2, the name is Mizakani, living is false, and so on. It has 4 records. Who here would be able, if I give you a paper and a pen or even on your computer, to convert what you have on the right to 4 JSON objects that correspond to the same data, 4 JSON objects that would be valid against the JSON? Who would be able to do that? Okay, most of you, very good. It would just be, for example, let's do the first one. It would be curly brace, ID colon 1, comma, name colon Einstein, comma, living colon false, close curly brace, right? And you can do it for the 4. So what do we learn here? We learn that for specific JSON schemas that constrain the structure in a certain way, once we have validated JSON documents against that schema, we are able to visualize it at something that kind of looks like a table. In fact, here it's exactly a table, right? So these 4 documents that we would validate correspond to that table. This is what we call a data frame. I will explain why data frame and not table, because it's actually more general than a table, as we will shortly see. Here's why it's more general than a table. Now, imagine that I slightly modify my schema, and the name now is an array of strings, right? So this is the JSON that corresponds to that. It's relatively easy to parse. So name is a sequence of strings. Do you see that now I would still be able to draw it nicely as something that looks a bit like a table? Imagine here, for example, that in my first JSON document, ID is 1. Name is an array of 2 strings. So that would be name, square bracket open, Albert, comma, Einstein, close square bracket, and then leaving false. Here we have an array of 1 string. Here we have again an array of 2 strings. And here we have again 1 string. Who would be able to give me the JSON for that? Okay, you should do it as an exercise if you cannot do it visually. But this is the idea that this is 1 JSON document, a second JSON document, a third JSON document, and a fourth JSON document, but nicely visualized like this. Now you see it's not exactly a table, right? Because you see the horizontal line here is only here, it doesn't go the whole way. So technically it's no longer a relational table, right? So this is what we call a data frame. And you can see that every column corresponds to a key. ID would just be an integer. Name would be an array of strings. So here you can have several, and leaving would be a Boolean. Is there a question on the Zoom chat? Would it be possible?
So there is a question on the chat saying that, would it possible to accept a string or an array?
In JSON, yes. So we support union types. It's also true in JSON schema. It's also true in XML. So you can absolutely build a schema that is flexible and that accepts at the same place a string or an array. This is entirely possible. But when that's the case, you can no longer visualize it like this in a general way, right? So there are a few constraints on the schema to be able to map it to a data frame in that way. I will tell you a bit later. But one of these constraints is that you cannot have unions of types. It really must be a specific type for every column, for every key. And again, in an array, you must have a specific type and so on. Right. So you are not allowed to use item, for example. You cannot say an array of items. It has to be an array of strings, an array of integers, an array of dates. Does that answer your question? Yes. Awesome. Okay, so this is the case of nested array, and here you see the vertical list of cells. Now, nested objects. Nested objects, I would have, for example, name that is now an object. First is a string and last is a string. The way we map it here is that it almost looks like a table, right? So this is ID1, name first Albert, last Einstein, leaving false. But the way we actually do it is that in the headers, we draw these lines, but then in this header here, I have a horizontal line here, and then first here, last here. So this is nested. First is nested in name, last is nested in name, right? And then leaving is again 4 Booleans. Who would be able to give me the 4 JSON objects here? Okay. If you can't, then think about it and try to do it as an exercise, because this is again a visualization of 4 JSON objects. But again, this is a data frame. Then we have an array of objects. Remember that the array of objects, that's for nested tables, right? So how can we have nested tables in this way? Who is an array? And every object in that array must have a key name that is a string and a type that is a string. It's optional, of course, but if the keys are there, they must be strings. And now you see in the data frame instance, what we have, the column ID, this is easy. The column leaving, this is easy, right? These are all integers, these are all Booleans. And now in who, I have a nested header name and a nested header type. And I also have these horizontal lines that don't go the whole way, right? So it means that here I have an array of 2 objects. The first object has name Albert type first. And then the second object in that array has the name Einstein type last, right? So it's an array of 2 objects. Here it's an array of 1 object. Here it's an array of 2 objects. And here it's an array of 1 object. Okay, for whom is that clear? right? And now you see these are in fact nested tables. This is a nested table. 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 But previously, when we had nested table, I put the headers of the nested table every time. But here, these are nested tables that all have the same schema. So this is why we put it here, the headers instead. Okay. So again, as an exercise, try to figure out the 4 JSON documents that would correspond to this data frame instance. It's a very good exercise. Okay. Now let me try to tell you the sort of constraints that we have on the JSON schema for this to work, because otherwise it doesn't always work. The first constraint is that you must have closed object types. You cannot have a schema that accepts unknown keys, right? It's these additional properties of JSON schema. So you must have a schema that doesn't allow for extra columns, for extra keys. Otherwise, you can no longer draw it so nicely. Optional keys are fine, right? Then you just leave the cell empty, or you just put a null in there. But basically, it would work. You must also have only what's called an instantiable type, and I will explain what that means. It means that here, I have integer, I have string, I have booleans. These are instantiable types, right? You can all have directly these values that are of these types. What you cannot have are 2 generic types. For example, you cannot just say item. Item is too generic. An item could be an integer, it could be a string, it could be a date. It is too generic. So this really requires that you put very specific atomic types from the menu in there, right? So this is the idea. And basically, it means that there is really a mapping between the notion of a schema of a data frame and JSON. You can actually use JSON to describe a data frame in this way. Now, there are schema languages specific to data frames, but it's not really standardized. We'll see that in Spark, there is a specific way of defining a data frame schema. There is another one in pretty much any library, in Pandas and so on. So there is not really a specification or anything. It's really highly dependent on the library that you are using. Okay, who is with me on that? Who has now this intuition that a collection of many valid JSON documents can be drawn in this way? Who has this intuition? Very good. So now when you see a data frame, think of it as a collection of valid JSON documents. This is really what it is. And a data frame is more general than a relational table because we allow for more nestedness, right? This wouldn't be a relational table, right? Because the headers are not relational headers. You have these horizontal lines that don't go the whole way. So it's more generic than that, and this is a data frame. Okay, we'll query them later. I'll come back to that with Apache Spark. We'll see how to query them, but this is the connection I wanted to make. Now, let's talk about formats. When we deal with trees, and it doesn't matter if it's XML, if it's JSON, if it's data frames, if it's whatever it is. In general, from an abstract perspective, what we have is a list of maps, a collection of documents. The collection is a list, right? A collection of things can be seen as a list of things. And every document inside that is a map, right? We saw that a JSON object is a map. It maps every key to a value. So from an abstract perspective, any data set that you download from the internet is going to be a list of maps, right? Now let's try to understand what these data sets look like and how we can classify them. A first way to classify them is to distinguish between flat data sets and nested data sets. That shouldn't be new to you, right? We've already discussed that before. In a flat data set, you don't have any nested structures. Every single cell that you have in there is atomic. You can have strings, dates, integers, and so on. Every single one of these 12 cells is an atomic value, nothing nested. We say that it's flat. We can have nested data sets that you can draw like this. Again, I could also put this name living up there together with people and draw it in that way, right? This is, again, then even more structured. But basically, here we have nestedness, right? So this is a nested data set. In terms of JSON, a flat data set just means that all the values that you have in your object are atomic. But in a nested JSON data set, you can have nested objects, nested arrays of objects, and so on. So the first distinction is flat versus nested. So this is what it looks like in JSON. On the left, you have a flat JSON data set. On the right, you have a nested JSON data set because you can see that people is an array of objects and it has further structure. What's very important is that this distinction is the same whether you look at this visualization or whether you look at this in the JSON syntax. You have exactly the same visualization. This here is the same thing, right? This is the syntax, this is the visualization. Okay? Here's another one. It's another way to distinguish. We distinguish between homogeneous and heterogeneous data sets. In a homogeneous data set, all of the records look alike. In a heterogeneous data set, you can have missing keys, you can have additional keys that you don't have in the schema. You can have also types that don't even match each other, like you can have an integer in a date in the same column and so on. This is heterogeneous. So this is the visualized version of heterogeneous, homogeneous. This is the syntax distinction. You see on the top left, you have a homogeneous data set, it has exactly the same keys everywhere. And on the bottom right, you have a heterogeneous data set because you have missing keys, additional keys, and you could even have different types for the same key across the collection. Okay, so that's homogeneous, heterogeneous. And then you can cumulate the two. So you can have a flat and homogeneous data set. That's actually a relational table. And on the right, you have a nested heterogeneous data set. Here you have everything. You have nested arrays, you have missing values. So you can see here, there is a missing value here. There is an additional value right there. Here it's also heterogeneous because in the same cell, you have a table and a string, right? So this is heterogeneous because these are two different, it's basically in JSON, an array that contains an object and a string, okay? So nested and heterogeneous. So this is the visualization of flat and homogeneous versus nested and heterogeneous. But again, you can also look at it in JSON, where you have on the top left a flat homogeneous JSON data set, and on the right, you have a nested heterogeneous data set. So you can see here what I was saying earlier. You have an array that has an object and a string, right? So this is heterogeneous, okay? So this is how you look at this data set. What I want to say here is that it doesn't matter if it's JSON, if it's XML, it's exactly the same idea of this nested, not nested, homogeneous, heterogeneous. It works in exactly the same way. And in fact, there is a whole universe of schema technologies and formats and so on that more or less follow these principles. You have some are allow for nestedness, some allow for heterogeneity, some don't. So there are many, many, many. So JSON and XML we covered. YAML, I only showed it to you during the syntax lecture. CSV, you know about it. This only does tables, so it doesn't, CSV, for example, doesn't do nestedness. Data frames cover nestedness, but they do not cover heterogeneity, because otherwise you run into issues trying to draw them. libsvm is for machine learning. This is also a structured one. Avro, Parquet, protocol buffers. This is by Google. Who heard about protocol buffers? It's by Google. It's basically a binary version of JSON and XML. So, but it's exactly the same idea. So you see, what I try to do in this lecture about data models is to teach to you in a generic way the notion of atomic types, the notion of schemas, and so on. I did use XML and JSON, specifically to show you how it looks like, but you really need to take a step back and understand that this is not particularly tied to XML or JSON, right? It might even be that in 10 years, there is another one that takes over, but the principles are there. You have a collection of documents that you can validate against a schema. So If you look now at the formats themselves, if you want to classify them, so here that was about the classification of data sets, right? But how we classify now the formats themselves. A format means, think of it as a file extension, right? PDF is a format. OpenOffice spreadsheets, that's a format, right? A text file .txt, that's a format, right? So think of it that way. .json is a format. .xml is a format, right? It's a data format. Now, we can classify these formats. Nested flat, CSV, for example, is a flat format. In CSV, you cannot have nested structures. JSON and XML are nested formats, right? Protocol buffers is a nested format. Data frames, that's also nested. YAML, that's nested, and so on, right? So nested versus flat, whether it allows or not for nestedness. The second distinction between formats is it a text format or is it a binary format? XML and JSON are text formats, right? You can open it in a text editor and see it as text. In fact, we spent an entire week looking at them as text. YAML is also text. CSV is also text. Protocol buffers is not text. That's binary. If I give you a protocol buffer file, you cannot open it in the text editor, right? That's fully binary, highly compressed and encoded. Parquet is binary. Avro is binary, and so on, right? So this is the second way you can distinguish. Why is it important? It's because typically a binary format will be more efficient than a text format, which is the reason why a good practice when you download a data set from the internet, for example, I don't know, from the website of the Federal Office of Statistics, you can download a JSON or XML and so on. But if you want to query it, to query that data repeatedly, and it turns out to be valid against some schema, then it's usually a very good idea to convert that data to a binary format. So a very common thing to do is to take, for example, a data set like the Great Language Game, you download it as JSON, and then you basically use a tool that converts it to Parquet, for example. Why would you do that? You would do that because the size of the file would be much smaller. If you convert the same data from a JSON format to a Parquet format, the size in bytes, in kilobytes, in megabytes will be smaller, and a lot smaller. So you save space. It also means you can squeeze more on your hard drive. You can have more data on your hard drive, but also it means that you can read more data every second, right? Because again, the bottleneck we will see when you look at MapReduce, the problem we solve with MapReduce and Spark is that we cannot read data fast enough. But if you save your data in a format that is smaller, then it means you can read more information every second because you compressed your data. So this is why these binary formats are in fact very, very useful. But they are very easy to learn because you know what a collection of documents is. You know JSON, you know the distinction between atomic types and complex types, arrays and objects and so on. You know that a data frame is a collection of valid JSON documents. So you basically know Parquet. I did not even teach you Parquet, but you know Parquet because Parquet is just a binary format for storing collections of valid JSON documents. In fact, collections of data frames, data frames. Okay, so that's the second distinction, text versus binary. The third distinction is whether or not they require a schema. Let's look at that. JSON and XML do not require a schema. You can, but you're not obliged to. If you don't want any schema, you can absolutely still use JSON and XML. YAML also doesn't. CSV kind of requires a schema because you need your columns, but on the other hand, CSV is not going to complain if you have mismatching types, right? It's just going to be hard to open in a spreadsheet software maybe, but so CSV is kind of in between. Protocol buffers do require a schema. Parquet does require a schema as well. That's how it can actually efficiently store it in binary. Avro also needs a schema and so on. Protocol buffers, in fact, it's kind of like Parquet, right? It's like the Google version of Parquet. It's a bit more complex than that, but basically, protocol buffers is also a binary format that stores collections of valid records, just like Parquet. All right, so you see, sometimes the schema is required, sometimes it is optional in the format, but there is a common a common feature is that usually when the format is binary, it does require a schema, because it doesn't really make sense to store something in a binary format if you don't have a schema. The whole point of the binary format is that with a schema, it can compress the whole thing. So that usually goes hand in hand to require the schema in a binary format. Now, what I'm showing to you here is not material for the course. I just want to show you that now that we've covered all of that, this type system for JSON schema, XML schema, if now you were to use one of these formats and you want to understand how it works and so on, you will look at the documentation. What I want you to see is that it's going to be easy when you do it. It's going to be very easy. And to show you how easy it's going to be, this is what you'd find in the Parquet documentation. You look at the Parquet documentation, what are the types? Now, of course, you're going to see these are names that are weird, right? So in 96, in 64, right, we didn't cover them. But if you look closer, you will actually see that this menu of Parquet is actually pretty similar to what we've seen, right? Look, you have Booleans, you have numbers. There are different types, but these are still number types. You have double, you have decimals. Strings, you have UTF-8, so this is just the encoding, right? But this is a string type. Binary, you also have a binary type, you have a date type, and so on. So if you don't focus on the exact names of the types and on the exact list of types, and you just look at it from far away, this is actually not new. It's just a list of atomic types, and the categories of atomic types are exactly what you would expect. You can look at any other like protocol buffers and so on, Avro, it's going to be the same. So of course, you will have to learn the exact types when you use it and look at the documentation, but the idea is there. If you look at the structure, so these are the atomic types of Parquet. What about the structured types? Surprise, surprise, it has lists and maps. It calls them list and map. But look, a list is just an array, a map is just an object. So that, again, makes it easy. Why do they not have 8 and 16 bits? I actually don't know. This is exactly the part that I told you, look at the documentation, see what they have. Maybe they have maybe they are there and I just didn't find them. Maybe they are not there, but that's just what you have. But the answer to your question is basically, I don't know, if I summarize. Yeah, okay. Again, this is like what I told you with Swiss German, right? It's like, imagine that I just told you Zurich, and then you go to Basel, and then they speak Baseldeutsch. It's slightly different names, but in fact, you can still understand what's going on. So it's like a different dialect. And here again, list and map, but again, lists are just like arrays and maps are just like objects. So Parquet basically has the same type system or a very similar type system to JSON and JSON and JSON schema and so on. And this is the reason why you can create schemas as well. And you can also store data that is valid against that schema. It's just going to be binary. This is yet another example. This is a schema, but in protocol buffers. But here too, you shouldn't be scared of anything because even though the exact syntax would be slightly different, let's say that's Berndeutsch, but if you look at the details, what do we have here? We have person that is basically a complex type, like a JSON object or a complex type in XML schema. It has four keys, last name, first name, title, and boss. These are 4 keys. And they have types. Last name has type string, first name has type string, title, that's again a complex type that would be defined somewhere else. Boss is a person, that's again a complex type defined somewhere else. And here you have this required, that's just like the exclamation mark in JSON, right? It's the, or the required in JSON schema. You have the repeated. Repeated would be either like a JSON array, or it would be like the max occurs unbounded in XML schema. Optional would be, that's the default in JSON, right? That it's optional. In XML schema, that would be min occurs equals 0. But basically, you have exactly the same features. It just looks different. It's a different syntax. But the idea and the way it works is exactly the same. So now, if you were to have a project that you work on and you need to use protocol buffers, that would be very, very easy, right? So this is the idea that some have schemas and are homogeneous, especially the binary formats, and some are heterogeneous. You deserve the break because now I talk so much that we are slightly over, but I'm done with the part on data models and the validation and data frames. I'll give you the full break. So I will see you at 19 past 9 to make sure you have the full rest, and we'll do MapReduce. Thank you.